Standing in the center of Zimbabwe's sweltering heat is a building that defies every rule of modern architecture. It is the Eastgate Center. To the casual observer, it looks strange. A heavy, brutalist structure of concrete and brick covered in prickly overhangs and jagged edges. It doesn't have the sleek, mirror-smooth glass facade of a New York skyscraper or the icy, hermetically sealed lobby of a Dubai hotel. But the most shocking thing about the Eastgate Center isn't how it looks. It is what is missing from inside it. You walk through its halls, and the air feels pleasant, cool even, not refrigerated or artificially crisp, just balanced, comfortable, almost natural. Eastgate Center has no conventional air conditioning. None. No sprawling compressors hidden in basements. No industrial chillers. No humming rooftop units. Nothing you would normally need to keep a building this large habitable under the relentless Zimbabwean heat. By all conventional engineering wisdom, the people inside this building should be baking. But they aren't. They're going about their day as if the building itself understands the climate better than the machines designed to control it. The question is simple. How is this possible? And the answer is almost unbelievable. It was stolen, borrowed from one of the least likely engineers on Earth, a blind insect. To understand the genius of the Eastgate Center, we have to leave the city behind and travel out into the open scrubland of the African savanna. Here, dotted across the landscape, you see them, termite mounds. They rise out of the earth like Gothic cathedrals made of red mud, some standing 20 feet tall, hard as concrete, enduring the elements for decades. For a long time, we looked at these mounds and assumed they were just big piles of dirt, a simple house for a primitive bug. But we were wrong. The macroterms Michaelsini is not a primitive bug. It is a master engineer, and that mound is not their house. The mound is their lung. You see, the millions of termites that build these structures don't actually live in the tower. They live deep underground in a centralized nest, and they have a very specific motivation for building these skyscrapers. These termites are farmers. Deep in the dark, wet core of the nest, they cultivate a specific type of fungus. This fungus is their primary food source. It digests the wood pulp the termites bring in turn, the termites eat the fungus. It is a perfect symbiotic engine. But this fungus is incredibly high maintenance. It is the Goldilocks of the fungal world. It requires a constant temperature of exactly 31 degrees Celsius or 87 degrees Fahrenheit. It demands high humidity and a specific oxygen level. If the temperature in the nest drops, the fungus stops growing and the colony starves. If the temperature rises even a few degrees, the fungus dies and the colony starves. This presents a massive engineering challenge. The outside world is volatile. On the savanna, temperatures can swing from a chilly 2 degrees at night to a blistering 40 degrees by noon. The termites are trying to maintain a laboratory-grade sterile environment in the middle of a desert climate. So how do they do it? For decades, scientists believed the answer lay in convection. The idea was simple and elegant. The sun heats one side of the mound. The warm air rises and escapes through the chimneys, and cooler air is drawn in from the lower tunnels. A natural breathing cycle, a perfect passive ventilation system. But later, research revealed the truth was even more astonishing. The termite mound is a dynamic lung. Air moves not because the mound is heated unevenly, but because the very structure acts like a porous membrane. Wind passing over the mound generates delicate pressure differences, pulling air through microscopic channels. Inside, the termites open and close vents, adjusting the airflow like living valves. The colony itself becomes a huge breathing organism, circulating gases, transporting carbon dioxide from the fungus gardens up and out, pulling in oxygen-rich air, stabilizing the temperature to that perfect fungal sweet spot. In other words, the mound is an industrial-scale HVAC system built by creatures with no formal training in engineering, a system that is entirely sustainable, self-regulating, and requires no external energy input. In the early 1990s, architect Mick Pearce faced a problem that would have crushed most designers. He had been hired to create a massive commercial complex in Harare. The investors wanted something modern, something impressive, something to bring Zimbabwe into a new architectural era. A building that could hold shops, offices, and large numbers of visitors. But Zimbabwe was facing severe economic constraints. Importing mechanical HVAC systems was massively expensive. Operating them would require huge amounts of electricity, which the grid could barely supply on its best days. And even if they installed the systems, maintenance costs would skyrocket over time. A glass office block would turn into a greenhouse within months. Pearce needed a miracle, or at least a radically different idea. And that idea arrived from the savanna. The story goes that Pearce had always been fascinated by biology. He studied local species, he explored African ecosystems, and whether he was watching a nature documentary or reading scientific papers, one fact caught his attention. Termites were doing something no engineer had ever fully replicated at scale. They were keeping a stable temperature in conditions far more extreme than the center of Harare. The termites, he realized, had already solved his architectural dilemma. The question was whether a human building could do the same. Pearce began to sketch not like an architect, but like a biologist translating anatomy into blueprints. He looked at the termite mound not as inspiration, but as a functional machine he could model. If termites use soil as thermal mass, he would use concrete. If termites circulate air through rising towers, he would build chimneys. If termites draw in cool night air to lower the temperature of their mound, the building could do the same. And so, the Eastgate Center was born. A building made not of glass and steel, but of heavy masonry, thick walls, deep columns, layers upon layers of concrete. Most architects see weight as a burden. Pearce saw it as a battery. Thermal mass, like the mound soil, would absorb heat slowly throughout the day. Instead of letting the sun blast through glass panes and fry the interior, the building would swallow the heat, like a giant thermal sponge, delaying its impact for hours. Next came the ventilation system. Pearce could not rely on termites opening and closing tiny tunnels, but he could use fans. Not massive industrial ones, just small, low-energy fans to nudge the air in the right direction. They would push warm air up into hollow chimneys, letting it escape naturally out the top. As it left, cooler air would be drawn up from the lower parts of the building, exactly like the airflow inside a termite mound. During the night, the system went into what Pearce called the night purge. When the air outside cools drastically after sunset, large volumes of that air are pulled into the building. It flows over the concrete, chilling it. That cold concrete then becomes the building's secret weapon. As the next day begins, the stored coolness slows down the interior temperature rise. It is the equivalent of starting the day with a fresh breath of cold savanna night air in your lungs. The building, in effect, had a metabolism. The building uses up to 90% less energy for climate control than its neighbors. 90%. That figure alone transforms the economics of architecture. And all of this happens in a climate where temperatures soar far higher than those in cities that waste enormous amounts of energy cooling down their office towers. Mick Pearce proved that the answers to our most complex engineering problems are often hiding in plain sight, scurrying under our feet. Since opening its doors in 1996, the Eastgate Center has quietly done its job, cooling thousands of people every day, year after year, without the machines we once believed were essential. As we face a future of rising global temperatures and expensive energy, we have to ask ourselves, why are we still building glass boxes in the desert? Why are we still trying to brute force our way to comfort? Don't forget to subscribe to the channel so you don't miss new videos. See you in the next video.